Kernel machines. Kernel machines are maximal margin methods that allow the model to be written as a sum of the influences of a subset of the training instances. These influences are given by application-specific similarity kernels, and we discuss kernelized classification regression, outlier detection, and dimensionality reduction, as well as how to choose and use kernels. Introduction. We now discuss a different approach for linear classification and regression. We should not be surprised to have so many different methods, even for the simple case of a linear model. Each learning algorithm has a different inductive bias, makes different assumptions, and defines a different objective function, and thus may find a different linear model. The model that we will discuss in this chapter, called the support vector machine, SVM, and later generalized under the name kernel machine, has been popular in recent years for a number of reasons. One, it is a discriminant-based method and uses Leibniz principles to never solve a more complex problems as a first step before the actual problem. Nick in 1995. For example, in classification, when the task is to learn the discriminant, it is not necessary to estimate where the class densities P of x conditioning on Ci or the exact posterior probability value P of Ci conditional on x. We only need to estimate where the class boundaries LIE lie, that is, x, where P of Ci conditioning on x equals to P of Cj conditional on x. Similarly, for outlier detection, we do not need to estimate the full density P of x. We only need to find the boundary separating those x that have low P of x, that is x where P of x is less than theta, for some threshold theta, which is chosen between the closed interval, the open interval between 0 and 1. After training the parameter of the linear model, the weight vector can be written down in terms of a subset of the training set, which are the so-called support vectors. In classification, there are the cases that are close to the boundaries, and as such, knowing them allows knowledge extraction. Those are the uncertain or erroneous cases that lie in the vicinity of the boundary between two classes. Their number gives us an estimate of the generalization error, and as we see below, being able to write the model parameter in terms of a set of instances allows kernelization. 3. As we will see shortly, the output is written as a sum of the influences of support vectors, and these are given by kernel functions that are application-specific measures of similarity between data instances. Previously, we talked about nonlinear basis functions allowing us to map the input to another space where a linear smooth solution is possible. The kernel function uses the same idea, for typically in most learning algorithms. Data points are represented as vectors and either dot product, as in the multi-layer perceptrons, or Euclidean distance, as in radial basis function networks is used. A kernel function allows us to go beyond that. For example, G1 and G2 may be two graphs, and the k of G1 and G2 may correspond to the number of shared paths which we can calculate without needing to represent G1 or G2 explicitly as vectors. 5. Kernel-based algorithms are formulated as convex optimization problems, and there is a single optimum that we can solve for analytically. Therefore, we are no longer bothered with heuristics for learning rates, initializations, checking for convergence, and such. Of course, this does not mean that we do not have any hyperparameters for model selection. We do. Any method needs them to match the algorithm to the data at hand. We started our discussion with the case of classification and then generalized to regression, outlier novelty detection, and then dimensionality reduction. We see that in all cases, basically, we have the similar quadratic program template to maximize the separability or margin of instances subject to a constraint of the smoothness of solution. Solving for it, we get the support vectors. The kernel function defines the space according to its notion of similarity, and a kernel function is good if we have better separation in its corresponding space.